Bismillah Rahman Rahim. So these are our objective for today class. Actually, in the previous lecture, we drive the Schrodinger wave equation, and this was like this. And here there are different parameters. Like here, this is the psi is the wave function, and this is very important for the rest of our all lectures because we will be focusing on this one and what would be the actually the value and how can we calculate the wave function in different movement of the particle or the electron. And today we will discuss about the translation motion, and here we will consider the case particle in one dimensional box. And here you will remember actually this is the total energy, this is the potential energy, and this is the kinetic energy operator. And that means the total energy is the sum of the kinetic energy and the potential energy. So here for the today lecture, we will be focusing on what would be the wave function in translation motion. So this will remain the same. Actually, Schrodinger wave equation. Now we are going to use this equation and to calculate the wave function. First, for today lecture, it is for the translation motion. And here the wave function, actually this is called the probability amplitude. That means amplitude of the wave, how much it is having the amplitude, that is called the wave function. And this is the final equation. Actually, we will be in two or three parts, we will be going to derive this equation, and then we will learn about what would be the significance of this equation, that is the wave function in translation motion or the wave function in particle in one dimensional box. And then we will consider on the another application of Schrodinger wave equation in translation motion to calculate the probability density. And this probability density is actually the density of finding the electrons. So you may have a keen knowledge in depth what about actually the wave function and where is the maximum probability of finding the electrons. And these are very two main important equations. Actually, these are the final equation. We will be uh, deriving these equation by using the Schrodinger wave equation. That's why this is called the solution of Schrodinger wave equation, and solution in terms of the translation motion, because we will be discussing the vibrational and rotational motion, and the same equation we will be using to calculate the wave function and the probability density. Actually, this is all about the quantum mechanics. Now you are going to further focusing on uh, what actually it is the wave function and where is the probability of finding the electrons. And for the translation motion, these are actually you will be studying the electronic transition. Actually, these electronic transition are comes under the translation motion, and this is the application of the Schrodinger wave equation. How can you calculate the what would be the energy difference between these two uh, energy levels, or the excitation of the electron, let's suppose from the bonding electron to the anti-bonding sigma, uh, and there is the pi bonding electron from the pi to pi star, or from the non-bonding to the sigma star, or the non-bonding to the pi star. So these are the possible transitions, and here you have a look, because the electrons is moving from one energy level to another energy level, and this is the direct movement of the molecule of the electrons present in the molecules. That's why this is called the translation motion. So it is in a particular direction. That's what this may be the x direction. So that's why we are going to consider the translation motion by considering the particle, and the particle over here is the electron particle in a one-dimensional box. And this you may consider this is the box having a fixed length, and there is the translational movement of the electron within the box. And this is actually the all these transitions are actually the outcome of the translation motion of the electrons. And we will be later on we will be calculating the how much energy is difference between these two energy level or their energy level, and what would be the wavelength. Actually, when you are getting the spectra from the UV visible spectrophotometer, so you will get a lambda max, and the lambda max or the other transition are coming from out of these different translation motion of the electrons, and or you can say these are the electronic transitions. So all these you will be calculating in the UV visible spectrophotometer. So now you are going to study in detail actually what is happening behind the electronic transitions, and what actually is the translation motion of the electron by considering the particle in one dimension box. So here now I'm going to start. Our first objective is the what would be the actually the wave function, and the second objective is the probability density. Actually this one is the, let's suppose this is the a box, and the this is the, here we are just going to consider one dimensional box, and one dimensional box is let's suppose the movement of the electron in x-axis here. And if it is also moving into the y-axis, that is called the two-dimensional. And if it is also moving to the z-axis, then it is called the three-dimensional box. So here, first starting with the very simple application of the Schrodinger wave equation to consider the translation motion, we are going to consider a particle. A particle, let's suppose, is the electron of mass m, is confined in this one-dimensional box with the length of L. So here x is, that means it is the x-axis, and it is starting, and it is the length of the total length of at the x-axis. It may be starting from 0 to going to infinity, but we have confined the particle within these limits, and limits are starting from x is equal to 0 when the, let's suppose this is the starting point of the particle moving into the x direction, and this x is equal to L. This is the second limit of the box. So starting here, ending over here, that's why this box is within the range of the length x0 to xl. And there are two important things to consider over here. When just to imagine that the particle moving along a piece of straight wire, like here, or in a one-dimensional box. And for simplicity, we are going to assume that this particle, actually the electron with mass m, has a zero potential energy inside the box. So here all about inside the box, the potential energy V will be equal to zero, for just to derive the equation, and then we will be more focusing on the this potential energy later on. So in one dimensional box, this potential energy is the within the box is zero. And what about the outside the box? Outside the box, it would be the infinity. We do not know how much would be the potential energy outside the box. So these are the limitation for the box. Within the box is zero, and outside the box will be infinity. And here it is a more picture, and when it would be the zero, the potential energy will be zero when this is in this range. That means when the this x will be greater than x, and less than L. So that means greater than X, it is starting from here to here, and the less than L, that means it should be less than at this point. So that is actually the dimension of the box. So it would be the potential energy is zero within the box. So outside the box mean when this X is greater than L. That means you have confined the a particle within this limit. And if the particle over here, that means this x at this point, the x is greater than L. So that means it is now outside the box, and then the potential energy will be infinity. And similarly, if it is the V is the less than zero, or then it would also be infinity. Less than zero mean now the particle is also out of the box, and the potential energy would be infinity. So within the box is zero and outside the box is infinity. And why I have explained in depth this potential energy, because we are going to use this assumption into the Schrodinger wave equation. So remember over here, this is the equation, Schrodinger wave equation we have derived in the previous 2 or 3 lectures, and I have requested you again and again to drive it yourself and look at each step, because all these steps are very interesting and should be understandable, that so that you can apply this knowledge to further apply the solution of the Schrodinger wave equation. So again, this is the total energy, this was the potential energy, and this is the kinetic energy. And with this concept, the particle in one-dimensional box, so within the box, the potential energy is zero. That's why this V becomes zero. So when V0 multiplied by the psi function, it will be zero. So the total energy will be equal to this one. Now, this is the our sorry, the first we have derived in the previous slide with the total potential energy is zero in with the particle moving in one-dimensional box. So I am now further going to rearrange, because if you remember the objective of this solution and the particle in one-dimensional box is we are going to actually find out what is the psi, the wave function, how can you calculate the wave function. So all these modification I'm going to do just to get the value of the psi, which is the wave function. So now moving to the this one, this is just the the rearrangement of this equation. And what is happening over here, this is the d square over dx square. This is a second differential, as we have explained in the previous lecture. So I am just going to get the value of this one. So when you get the value of this one, this is going to multiply and this h square is going to divide. So this equation will become like this. And similarly, to multiply with the minus, so minus is going over the right hand side and minus is here. Now, for the simplicity, this whole factor, and you remember this was our the kinetic energy operator, a pi square m over h square. Let's suppose this will be equal to the k square, because this all are the constant. 8 is the constant, pi is the constant, mass is the mass of the electron is constant, and this is h is the Planck's constant. On all these factors are the constant. That's why I have taken it into another constant that is called the k, and this is this whole factor will be equal to k square. So now I am going to put the value of the k square in this equation. Actually, this is the replacement of this whole factor with the k square. So by putting the k square over here, this equation will become like this: d square psi over dx square equal to minus k square psi, and this equation becomes like this. Now, more important here is the what is the k. And remember, this will be, I will be using different values of the k and in the next of the lecture. So all these are very important because here let's suppose we started with the Planck's equation is equal to h mu, and now the energy is like this, and there are several other, we derive the quantization of the kinetic energy, and in this application we will be also going to calculate another form of the energy difference between different energy levels. And all these are the actually the giving you more explanation about the energy or the constant you are going to use in the equation. So that's why this is k is one of the form, and we will be calculating another equation or another value of the k in the coming lecture. So here, what is the value of the k? Let's suppose this is the k square will be equal to this one, and the k will be, you can take under root over both side, and k will become like this. And this we have already explained before. H bar will be equal to h over 2 pi, and when you take the square it will become h square for pi square. So this is just to make it more simpler form. When you put the value over here, this equation will become like this, 2m e over h bar square. So this is the reduced Planck constant, and you may have further, if you want to know the explanation, you may watch the previous video as well. So this is the, this is an okay, rightly you can say this is the value of the k, and this is also the value of k. There is no difference between this equation and this equation because everything is the same. Just it is, this equation is more simpler as compared to this one. So moving to the actually the now the derivation about the psi, and in the Schrodinger wave equation we use the this angular movement of the electron, and having this radius, and this was the psi, actually the probability amplitude, that is called the psi. The distance is travel from here to here, and this is main the same explanation over here. And as soon as it will reach over here, then the amplitude will become like this, and then similarly the wave is going to complete with the movement of the electron in a circular path, and this we have already discussed before as given over here. Actually, this is the harmonic motion, and that means back and forth through an equilibrium, and it is moving here or to this side, and the total angle is covered by the 360. And this was, we discussed detail, and how we get the this equation in with these starting the derivation of the Schrodinger wave equation. So I am not going to repeat this one. I'm going to show over here because we will be using this one as the starting point to further explore the value of the psi. The psi over here, but in this case we didn't know what is the value of the a, and here the a is actually it is going to represent over here, it is the radius. But for the, there are the movement of the electron in several orbitals, so how can we calculate the radius of the particle or the electron moving in a specific orbit? So we do not know. So actually that is the application of the Schrodinger wave equation. We are going to calculate actually what is the value of the constant over here and constant over here. So moving to the our main uh, discussion or the derivation of the equation. Let's suppose this is the particle moving in one dimensional box. This is the x direction, and this is the wave function. Wave function here, you simply say this is the amplitude of the wave, how much it is making the distance from this x access to having this distance. And there are mainly there are two waves, and one we call that is the real, that is the purple, this is the real wave, and the other one is called the imaginary waves. There are two waves, that parts of a free particle wave function corresponding to the motion towards the positive x. That means if it is moving to the x direction, so this may going to produce two waves. One is called the real wave, which is in purple over here, and one is called the imaginary wave. So these real and imaginary just a description over here, but these as explained over here, this the both real and imaginary parts of the wave function, and of course these are the real. So these are just giving you the uh, actually the difference between these two waves we are going to label with. One is the imaginary and other one is the real, but in a sense the both wave are real in nature, and we will be actually using this one to further explore the properties of the wave function. So this was our previous equation which we have derived by using the Schrodinger wave equation, and that was psi equal to a sine 2 pi x over lambda. And here these are actually the two waves. One is representing the sine x and other one is the cos x. So I'm going to start with these two, and sine x we have discussed in detail in the Schrodinger wave equation how we are getting the sine, and there I also explained what is the cos. So here I am going to use both sine and the cos to discuss the movement of the particle in one dimensional box. Let's suppose this is the here the imaginary wave will be equal to minus sine x as it is indicated over here. So sorry, this is the uh, imaginary wave equal to sine x. And in the previous slide we have discussed the k over here. This was the actually the k we discussed over here. That means I'm going to replace a sine kx. This would be 2 pi over lambda will be equal to k. Or you may understand in another way. Let's suppose this is the constant 2 pi over lambda, and 2 pi how it is coming out I have already discussed in detail in the Schrodinger wave equation. And here this is the constant, pi is the constant, and the wave length will remain the constant for a particle moving in one dimensional box. So this will remain a constant, and let's suppose this will be equal to k. So if this is the k, and sine a sorry psi will be equal to a sine kx, and this will remain the kx over here. So just I'm going to correct this one. This may be the sign over here. So okay, so this is I have made the correction because this is actually the real both equation. So this is the constant, and constant is the k, and by using the constant uh, you are going to calculate the lambda. Lambda will be equal to 2 pi over k, and now we can recognize that the cos kx or sin kx is the wave length, is the wave of the wavelength that will be equal to lambda over 2 pi over k. So actually what is written over here, actually this k will be equal to 2 pi over lambda, or the lambda will be equal to 2 pi over k. If you know the value of the k, you can calculate the lambda over here. So this equation will be making to the another form of the equation, and that will remain the same as I have explained over here. So when you put the value of k, this equation will become sine psi will be equal to a sine x as given over here. So this was the Schrodinger wave equation when you put the value over 2 pi over lambda k, and this will be sine psi will be equal to a sine kx as indicated in this equation. So this is the one form of the explanation. Now I'm going to use another alternative explanation how we are going to neglect the cos kx and keeping the sine kx with rest of the derivation, and we are not going to use the cos, but we are going to use the sine. So here it is the explanation. So total wave function, as it is the indicated over here, the total wave function will be the sine kx and plus cos kx, because both are the real. One is by name, one is the imaginary, and other one is the real. But the total wave function will be the sum of the wave function of the sine kx and the cos kx. So that's why I have put over here psi will be equal to a sine kx plus b cos kx. So how it is going to be converted into the this form? So by using the this one, probability finding particle at either end of the box is zero. Just leave whatever it is explained over here and look at the this dimension of the box. These are the limits of the box, that means particle within the box over here. And what is the probability density? So this is the actually the area over here, and you may are going to visualize this is the dark shade over here and dark shade over here. This is giving you the indication that the maximum probability of the electron is over here. That means the area under the highest peak that is having the maximum probability. And if you consider this wave, and that means here the dark shade is here, and this is going to give you the probability of finding the electron under this peak. That means the maximum probability is over here, and the minimum or zero probability will be at the end of the box. That means at the starting point and the at the end of the box. Here you can see there is no any pink uh, dash or the shade over here. So probability of the finding the particle at the either end of the box at this or at this will be equal to zero. So both pi 0 and the pi L, sorry, psi 0 and the psi L are 0. Psi 0, that means when x is 0, and this psi L mean when x equal to L, as we have explained in the previous slide, the dimension of the particle in one dimension box. So both these are will be equal to 0. So I'm going to put the value over here. So for x equal to 0, we have sine will be equal to 0. So that means x equal to 0. I'm just putting the x equal to 0 and here x equal to 0. So what is happening over here when and at the x or L when equal to 0, the psi will be 0. That's why the put the value of the psi over 0, a sine k and x is 0, and b cos k and x is 0. So when you solve this equation, so a sine kx and plus b cos kx, this sine 0 will be equal to 0. So and cos 0 will be equal to 1. So 0 multiplied by k will be the 0. When you take the cos 0, that will be equal to 1. So here k multiplied by 0 will be 0, and when you take the sine 0, that will be equal to 0. That means this whole will be become 0. So b will be equal to 0. So when you put the value of b over here, so actually we have calculated the value of b when b over here. So b 0 multiplied by the whole factor will become 0. So net equation will be psi will be equal to a sine kx. So this is the second explanation that why we are going to keep this only the simple form of the the psi and why we are going to consider on the sine kx, not the cos kx. So this is all about the reason I have explained over here. So I am just going to wind up the lecture because we have only 3 minutes are left to end the meeting, and then we will be discussing and taking your question again. So now I'm going to differentiate this equation, and this again I have detailed discussed in the Schrodinger wave equation. What is the sine x will be equal to cos x. So sine kx, again k will remain sine, k sine will become the cos, and here this is the actually the whole this is the constant and x is the variable, and this whole theta will remain the constant, and just going to change this sign with the cos, and this will remain the same, and a will remain the same. And when you differentiate the x, actually x power minus x, uh, x power 0, that will be equal to 1. So that's why here only the k is k multiplied by 1, only k is left, and that is the k a cos kx. And with the second derivation again, as indicated over here, cos kx will be equal to minus sine kx, minus sine x. So this is the symbol for the second derivative, d square over dx square. Psi will be equal to, now again when cos will be equal to minus sine, this will remain the same. And when you differentiate the x, and this whole factor of the constant, x power minus 1, so x power 0, 0 sorry, x power 0 will be equal to 1, and 1 multiply k will remain the k. So k we already have over here, and then it become k square. So this equation with the second derivative will become like this equation. So this is all about our today lecture, and I will be using this equation, the second differential form of the equation, to further uh, discuss the value of the k. Actually, now again we will be calculating the value of the k and the value of the a are important, and by using these value we will be find out what will be the wave function, that is the psi. So psi will be equal to a sine kx. Actually this is the unsolved equation, and when you put the value of a and the k after solving the equation, then you will be able to calculate the psi function or the wave function with the exact parameter written over here, and then you can calculate the amplitude of the wave by using this equation. So with this I am going to end, and you are requested to join me again, so I will take your question. So with this, join again and discuss to the any question if you are having.